Hi, everyone. I'm Tom Hall, a sales engineer at Innovative Sensor Technology USA Division. I want to thank you for joining us for our discussion on liquid flow sensing and the new OOL module from IST. The presentation today will be a little under 30 minutes, and we'll wrap up with a Q&A session. I'll first introduce our company, IST. Then we'll start the flow presentation with a short video introducing the OOL module, and then we'll talk about the operating principle of the flow meter. Finally, we'll go over the specs, then open things up for a Q&A. Please feel free at any time to submit your questions or comments in the chat, and we'll go over them after the presentation. If we don't get to your particular question, we'll be sure to follow up later on with our feedback. First, a little bit about IST. Innovative Sensor Technology, ISTAG, designs and manufactures thin and thick film physical, chemical, and biological sensors. Here you can see our headquarter facility in the Toggenburg Valley in Switzerland. We've been in operation for just over 30 years now, and as of this year, we have around 500 employees across all locations. Along with our standard product offerings, we also make customized sensor and module solutions. Now I'll give a brief overview of the flow components that we make. We have several sensors for gas flow measurement. You can learn more about these on our website or in our general flow webinar recording. At the top, we have the FS, which covers a wide operating range. Then the microflow sense, or MFS, which features a thin membrane structure for fast response time. And the silicon flow sense, or SFS, which also has fast response time and is good for low power applications. As I mentioned before, these are for gas flow applications. Today, we'll focus more on the liquid flow measurement side, and we'll highlight the OOL, which you can see at the bottom left. Let's kick things off with a quick 2-minute video where we'll see the OOL module in action.
This is Leo. Leo is a machine operator. The machines he operates are temperature controlled by an external cooling circuit. An inadequate temperature control can cause a machine to overheat, which may lead to the production of faulty parts or even a machine failure. Locating the issue, making maintenance adjustments and repairs causes extensive downtimes and is stressful and expensive. It is crucial to recognize process deviations immediately. There is an easy way to prevent costly downtimes and monitor temperature and flow rates of your coolant. IST's OOL mass flow meter. The device continuously monitors your temperature control system and instantly recognizes deviations from set points. IST's OOL mass flow meter can be used to monitor each machine individually. Different set points ensure optimal process control at all times. Whether applied inline or with a bypass installation, a high dynamic flow range is covered. Using OOL mass flow meter to monitor the temperature control system, Leo can easily check its status and report process conditions during sensitive production runs. If temperature or flow rate exceed a certain threshold, a warning alerts Leo. He can examine the machine and prevent any malfunction. IST's OOL mass flow meter is suitable for a wide variety of industrial applications. It is a long-term stable sensor. Its stainless steel is the single wetted material and highly resistant to corrosion. It has a sturdy IP65 rated housing that makes installation into existing circuits easy. The OOL thermal mass flow meter is exceptionally reliable under industrial conditions to detect, monitor, or control flow and temperature. IST's OOL mass flow meter is an easy and low-cost solution to optimize your process and minimize machine downtime. Sounds exciting, doesn't it? Contact us now.
All right. So why would we use a flow module like the OOL? You might be trying to measure the rate of liquid flow or detect a leakage, or perhaps you're looking for something to monitor or control your processes. In each of these areas, the OOL offers a unique contribution. For example, in the area of detection, the OOL has excellent sensitivity, especially at low flow rates. For monitoring, one might install these in different machines with different settings per machine, like in the video. The key contribution here is the reproducibility, which can be critical in dosing and other applications. Lastly, we think of control. Let's say you're controlling your flows using valves or some other actuator type. By using the reliable flow data from the OOL, you can control your flow more efficiently and optimize your processes. So we know that each application area is pretty unique and things can get complicated quickly. So with the OOL, we want to expand our customers' toolbox so they don't need to spend time and energy reinventing the wheel when they're measuring their flow. Let's take a look at an example here of how the OOL might be implemented. Here we have a house with a dripping bathtub faucet. You can see at the top left of the image, which has a very small leaking rate on the order of milliliters per hour. Here we have the OOL module installed in a bypass configuration on a pipe going into the building. With all our faucets turned off, we'll still have a very small flow of water going through the pipe and the OOL due to the dripping faucet. Since the OOL has high sensitivity in the low flow range, we'll be able to detect this leak. This leak detection method can potentially replace more extensive pressure testing. Before we go into how the OOL works, let's brush up on a few terms. First, we have the velocity, often expressed as meters per second. This is the speed at which particles move through our channel. Volume flow relates to the velocity via the cross-section of the flow channel, in this case, our pipe diameter. This might be expressed in liters per second. Lastly, we have the mass flow, which relates to the volume flow via the density. This is the mass flowing through our pipe. This might be shown in kilograms per hour, for example. With the OOL, we'll be measuring the velocity, but since we know the diameter of our pipe and the density of our liquid, the results will be delivered in kilograms per hour. It's also useful to know the difference between laminar and turbulent flow. The laminar flow, which we picture on the top, is more suitable for measurement with the OOL. So this is worth considering when you're configuring your installation. All of IST's thin film thermal mass flow sensors use either the anemometric or calorimetric flow measuring principle. If you'd like to learn more about these flow measurement methodologies, you can check out our general flow webinar on our website. The OOL module works using the anemometric principle. To sum it up, we have an RTD temperature sensor, here we see it on the left, and a heater mounted on the outside of our stainless steel tube. We specify a certain temperature difference, which we'll be constantly maintaining by adjusting the power to the heater. As you can see in images 1 and 2, as the flow rate increases, the heat is dissipated more and we apply more power to the heater. So we have a relationship where higher flow rate means more power to the heater. The reason we apply this higher power is to maintain this same temperature difference at all times, regardless of the flow rate. On the right, you can see an example curve of the power applied with respect to the flow velocity. We have a few things to point out here. Since we have the RTD on the tube, the OOL not only delivers flow information, but the temperature of the liquid as well. And since the module has no moving parts, it has excellent long-term stability and reproducibility. With the anemometric principle, we rely on King's law. Here's a simplified version of the equation, which is explained a bit further in our application note. It gives us the power which is delivered to our heater for different flow rates. As you can see with the water example on the right, the curve is dependent on our liquid temperature, the flow behavior of the liquid, and the liquid type. So here we can see the temperature of our liquid at 5, 25, and 45 degrees C. And you can see how the sensitivity is slightly different for each, and the curve follows a different profile. Our standard OOL module is calibrated before shipment using water at different temperatures and flow rates. The calibration data is stored on board the module, and the signal is linearized and the temperature is compensated. At the end, our output is delivered as mass flow in kilograms per hour. If you have a different configuration in mind or you're working with a different fluid type, let us know and we can discuss your application in further detail. You might be thinking, what if I'm working with a liquid that's not water? So something different than what we're calibrating with at the factory. With proper calibration, the OOL can work for a variety of liquids, including cooling fluids, which might be water and alcohol mixtures, like in our video example, food and life science solutions, cleaning liquids, including chemically aggressive ones, oils and fuels, and even clinical and analytical samples. So we know that different liquids have different thermal conductivity and heat capacity properties. What do we actually need to change with our measurement when working with a non-water liquid? In this example, we see how certain oil compares to water. In order to get comparable sensitivity, we need to use a larger temperature difference. In this case, we set it to 22 degrees C instead of the 8 degrees that we were using for water. You can see on the right side plot that our curves look quite similar once we adjust the temperature difference. So this is something the user can do directly with the OOL module. You can change the delta T that's being used for operation. There's also a few other installation matters to consider when working with a more viscous fluid than water. In this example, the viscosity is higher for the oil, so we don't need as long of an inlet channel for the laminar flow. There are several different ways to measure liquid flow, so here I'll highlight a few advantages of using a thermal mass flow measurement scheme. On the left, we have the OOL sensor, which we've been making for many years, along with evaluation electronics. This consists of two thin film chips on ceramic substrates, a PT1000 temperature sensor, and a lower resistance heater. The chips have a metallized backside and they're soldered directly to the stainless tube. This gives us optimal thermal coupling and the fast response time. This setup gives us the ability to measure both flow and temperature because of the onboard RTD. It's corrosion resistant since only the stainless steel is in contact with the liquid. And it's also suitable for different flow types, including viscous media or media with particles. Additionally, with this robust setup, we have minimal pressure loss. I have one here. I hope you can see it in the camera. In this case, it's a 4mm tube. We have the heater with the red wires and the RTD with the white wires. Both chips are the same size and they have the metallized backside and they're soldered on like this. Some different tube diameters are available depending on what flow rates you're working with. But in this case, we have the 4mm is pretty standard for us. On the right side, we have the OOL mass flow meter. Inside, it uses the same type of OOL sensor, and it covers a dynamic range and is very sensitive at low flow rates, making it a great choice for leakage detection and dosing. It comes factory pre-calibrated and delivers a digital I²C symbol with temperature in degrees Celsius, the raw power in milliwatts, and our flow rate in kilograms per hour. It offers a great price-performance ratio and is simple to install in many applications. And like I mentioned before, no moving parts. Let's take a look at the specifications of the OOL. With our standard water calibration, it covers a flow range of up to 20 kilograms per hour with 3% full-scale accuracy and fast response time of around half a second for T63. The module can be operated with fluids ranging from 5 to 50 degrees Celsius with better than 1 degree C accuracy. The standard version uses a Type 304 stainless steel, which is good for most industrial applications, and we can change to a different metal type or a different diameter. If your application calls for something different, just get in touch and we'll recommend something that works for your case. Here we have a drawing of the module. The module is pretty lightweight, weighing in at just 140 grams and has a relatively small footprint. I have this one here, like I showed before. Here we have our flow inlet and the outlet, some mounting holes, and our connector here for our data output. So it works in many installation configurations, but we usually recommend having it horizontal like this, or if you want to install it with the tube going vertically, you want the arrow facing up and your flow going that way. That'll give you the best behavior and the best response. So after the presentation, I'm going to send out a few pieces of information. We have the data sheet, application note, some photos, drawing, and step CAD file is available upon request. I'll also send out today's slides, a link to our web shop where you can learn more about the OOL. And I'll also send out my contact information if you have any questions or you want to discuss your application further. Let me just give a quick overview of the 3 documents I'll send out first. So here we have the application note, which walks through just a general description about the OOL, some of the key features, the measuring principle, more details about the sensor inside, the housing, King's Law, calibration, etc. We have our data sheet, which includes the drawing, all relevant specs, and more information about the I2C protocol that the module uses. Then an I2C description, which goes a little bit more in depth about the communication protocol that the module is using. All right, that wraps things up. Now I'd like to open up the floor for questions. Feel free to put your questions in the chat and I'll do my best to answer them. If I don't get to your question or it requires further support, I'll reach out after the presentation with our feedback. You can also reach out to me anytime by phone or email, and I'll put my contact details into the chat now.